Thank you for joining us today. I guess people already know my first slide. It's always the brave story. The brave story is now a 5-year-old story, and we are still as excited as we are at the beginning. And today it is really about optofluidic force induction plus Raman and what you can really do with it in microplastic particle characterization and analytics and beyond. It's really a new way, and we call it a brave new way for continuously analyzing plastics and getting information as a count-based method. It's a really new approach, and I want to guide you through, first of all, where does brave come from? If you do not know brave yet, I want to give you a little bit of our background. I want to give you an introduction in where do we come from, and then give you an introduction of what do we do with our OF2I Raman technology. How does it work on a little bit more technical question? What kind of specification and definitions we have defined yet for OF2I Raman? And then, of course, really diving in what you can do with it and how can we solve problems people currently face in microplastics analytics, getting, of course, also into different use cases, tell you what we have done with different of our customers, and of course also tell you a little bit about our next steps and challenges, because each and every technologies has advantages and disadvantages. I also want to talk a little bit of this and then give you a summary. And then, of course, I'm very excited for your questions. Why it's critical to know more about micro and nanoplastics. I think this is one topic I don't have to talk too much about it anymore. There is a concern out there that microplastics and our environment facing these threats of producing more of degradation products from plastics called microplastics are affecting our health, not only for humans, for animals, but also our ecological health. And in order to really understand this and face the challenge of studying their health risks, what kind of effects do those particles have? What kind of information can we get in food, in water, in air? How do we quantify this threat? And also, how are we exposed? We really need to think about how to get into analytics to get all this information. And why do we need it? Well, we need regulations. If there are actually risks out there, we really need to assess those risks. We guide regulations. Then, of course, have information for how to have better waste management, new material designs, and so on to really tackle this challenge. The EU has already started looking into this, and there are a couple guidelines out there already, starting with the Drinking Water Directive, Urban Waste Treatment Directive, and also Water Framework Directives. And there are suggestions out there where you should report on drinking water contaminations, where water treatment plants need to report. And our EU action plan, for example, towards zero pollution for air, water, and soil, and the Green Deal also really mentioned 50% reduction of plastic litter at sea and minus 30% of microplastic released into the environment. So to really monitor this, we need to have analytical methods and to see what is the risk and to have countermeasures available. Where do we come from and how do we want to help on doing this is really, well, we are a spin out from the Medical University of Graz. The Medical University of Graz is in Graz, it's the second biggest city in Austria. We are 2 hours south of Vienna, and we are coming from biophysics and pharmaceuticals. With this, we sit here right now. I sit here, give this seminar. And if you're in Graz, I always tell the same thing. Please come by, stop by, have a coffee with us. We can show you the devices, how it works. And we can, of course, talk about your challenges and how we can tackle them together. Right from the beginning, we designed our brave mission, and coming from the Medical University of Graz is really advancing human well-being. So really a medical approach, I would say, but based on our technology, we really also want to ignite curiosity by providing deeper insights into particle processes. So micro nanoplastics really do belong in there, and driving innovation and ensure a healthy and safer world. I think right from the beginning, this topic fit to our mission, but it was not how we started out at the beginning, because at the beginning, we really looked into pharmaceuticals, and we are still looking into pharmaceuticals. So production of infusion or parenteral nutrition was one of of our topics to really look into nano characterization over time, so-called PAT sensors, where we have single particle based information on liquids containing particles. So really in the nano space, but having the really nice advantage of seeing very low concentrated populations when they appear during a production. And we were able to provide characterization and technology or characterization values over time to really give process information, have a clear approach on using this information to reduce lost patches, but also give clear and stable production monitoring for quality assurance. With this, we of course thought right away, how can we make sure that everything we do is really based on a NIST traceable standard and has really a physical principle behind it. So we were always looking for materials where we can prove that what we do on our physical models is really something not only our physical models as a parametric-free model works, but also it works in real life. So we compared it with different characterization technologies right at the beginning, even though not having raman-analysis yet included, but still using Thermo Fisher Scientific NIST traceable standard materials to really prove that we can do what we can do. The thing is, when you create a new principle, and OF2I, we call our new principle, you really need to prove that it works. And the first, I want to give you a short summary or short introduction what OF2I really does. It works with particles in liquids. And those particles we really pump through a capillary. This capillary is creating a laminar flow, and it's roughly 1.5 centimeters long, 1.5 millimeters in diameter, and we create a laminar flow in there, so we know exactly how, when we pump particles through here, how they flow, how fast they flow, and what is their transportation through the capillary. On the other hand, you see it here already, we create a light tube, a laser force field, creating a second force component on the particles. So first we have the fluidic forces transporting them, and with this second laser, we create a force field, an optical force field, so a laser tube inside this glass tube. And this laser tube has now a couple challenges. First, it traps the particles on this light surface. So they are really trapped and located on a certain spot here on this surface. And because of this, they also start to scatter. So the nice thing is that because they scatter, we can observe them when they flow through. So each stripe is located on this surface, is trapped on here, and we can now observe particle velocities and scattering data. And this scattering data tells us about the properties of the particle, and the velocity tells us another property, size and size distribution. And by gathering all this information, we can do this over time. So it's really a flow-through principle, creating this information, and this laser task now really changes the speed of the particles because it induces forces. And this is why we call it Optofluidic Force Induction, where we push particles via a fluidic force and then change their trajectory via optical forces, but also collect the scattering data during this process. So OF2I principle is a parametric-free model, so it can really be calculated for the particles, and it is based on this physical Nobel Prize in 2018, where Mr. Arthur Ashkin thought about light as a tool. He really manipulated nanoscale objects, so really creating these optical tweezers, and with these optical tweezers, he really was able to trap particles. He was able to really define where they're located, squeeze them, manipulate them on a very precise scale. And he figured out that this is really a tool to create a new tool in this very biophysical material, because it's very precise and it can be calculated, and it can be really useful to look into cells, to look into particles. He did it on a single particle base or a couple particles. And what we do with OF2I now is really doing with lots of particles at the same time. So this fluid channel, we really look at this center here, and when particles are trapped, they are trapped out here and are transported into our observation window. And this is where we get the information from. So you have the particle flow. It can be in both directions. When it's with the laser propagation particles like here, they really start to accelerate. And when they're against, they start to deaccelerate. We will look later on why we can use this information then and also have better information about the nanocharacterization and analytics. So with this, we unfortunately can only get information on size and concentration, so at the amount of particles, but we cannot see any analytics yet. So how can we characterize those particles and look if they are nanoplastics or not, or microplastics? And this is what we basically use for the characterization. We have this information available, we can calculate this, but the analytics really comes from this information. So there, the Rayleigh scattering really helps us to identify where the particles are. And then we really use each stripe and put the light from a stripe into our specially designed Raman spectrometer. This Raman spectrometer creates now for each stripe, so the stripes are located down here. This is along the capillary, a Raman shift. And this Raman shift basically really goes and gives for each particle, so it's very early, it's one of our first signals actually we show here, along the frequency on certain signals. And here you can see already some brighter and some lower peaks or information on our camera. And it gives indication, yes, there are different intensity or different peaks coming from this shift. And with this Stokes-Raman shift, we have now really the possibility to get information on single particles and create this Raman spectrum as a continuous working Raman flow-through tracer. And this is really the topic or the technology behind which we use to do lots of things. We are now able to really see, because first of all, are at a certain Raman signal is very low, so we cannot really go down to 100 or 200 nanometers yet for getting this information, because the Raman-Stokes scattering is very, very small. But for the bigger fraction, for us bigger, so to say, it is possible. So going from 1 micrometer and beyond, I will show you then later, we can really identify the particles and get information what materials they are. And this is the really nice thing, that we can do this automatically as a flow-through kind of principle. Here, particles are flow through. We already have the software from our previous information on characterization that we can track them. And now we really push them, or they just flow through, and we collect the spectra. So with this information, we thought, hey, it is very helpful to measure contaminations. And this is what we did first, that we really used this whole new approach to have a sample in, sample through, and sample out, as so optical flow-through trapping, and to use this Raman, inelastic Raman scattering to get the material identification. So size distribution, particle concentration, and particle identification is available. We then put all this into a device and made some feasibility studies with pharmaceuticals first, because this is where we came from, and said, okay, from now on, we can not only see what size and size distribution there are, but you can clearly say, these are the normal particles, so your normal population. And when you have contaminations in there, we can see it and see, oh, this is with this, for example, occurrency, we can tell you there's something really, there's wear, or there's some other particles coming from another source, their filtration bleeding, and so on. So the use case was really to find contaminants at the beginning in a product like pharmaceuticals or biotechnology and so on. So it really helps to give production managers indication for predictive maintenance, find faulty materials, and find wear in different tubes and so on. When we then presented our spectrum, like having this characterization, as well as the B-elementary to really go from a size range from roughly 250 nanometers to 50 micrometers for our Raman spectra, we looked, as I said, into different behaviors. So low concentrated particles were always a topic. Where do they come from? Can we filter them out? And we were able to really detect them also without analytics and see, oh, a filter really works. We can take out these low particle concentrations, and we are able to use this technology to measure them. We were able to also define only on the size at this point in time back then that a microplastic filter, for example, works, because we were able to measure the size fraction, see how many particles you have coming in a certain microplastic size, like 300 nanometers, and then measure how many are coming out from the same size. But at this point, we were not able to really get the information on the spectras. But now we really said, okay, with the spectras, we can not only get the information on the particle size information and the concentration, but also really define how many particles of these coming through are really leaching or contaminations or are really spectra. So we were able to define particles very fast. And back then we did not know how fast actually our system works, because we used, for example, this 5 micrometer standard, and we could really clearly identify their material on lots of particles in real time. And when we presented this to different people, we are able to get below 20 micrometers in real time and measure directly in liquids, contaminants, but also the plastics. Then people approached us from environmental. And this is how this whole story of Brave got into a microplastic detection, because coming from contamination detection, the same problems exist also for microplastics. Of course, with our single particle Raman spectroscopy, if you have a clearly defined sample in pharmaceuticals and you only look for contaminants, you only have two populations, so to say. So when we started to look into microplastics, there were a couple more challenges. The challenges first on the technology side were, well, of course, there are some other technologies out there to really determine them. And FDAR, with their current size limits, their challenge is really to go beyond this 20 micrometer or 5 micrometer size regime to clearly define the material. With Raman microscopy, for example, it's really coming, they can have lower results, but they struggle going beyond this 5 micrometer with their time scaling, because it really takes days or weeks to have this resolution in size and in identifying, for example, a microscopic filter to get down to this kind of sizing. And there are other technologies out there which are unfortunately not optical anymore, so that you lose the information of the particle count because it's really destructive, and you get mass information, and via this you basically estimate the count or the sizing. So the sizing is not really available on a single particle base anymore. And this is not to be underestimated, but you probably know all these challenges, that you have a very heterogeneous particle system. So size distribution, material composition are not as defined as in pharmaceuticals. So different challenges appear. Same with sample quality. Some samples are very defined in the matrix, or are degraded, and you really need to look into spectra differently, because yes, there are clearly defined degradation from UV or ozone, and all this needs some help to really go into lower than 20 micrometers. And the last thing, I think what we noticed is really the sample preparation steps. We underestimated what other technologies really need in order to have the sample filtrated on this filter, for example, and have a clear approach on how now we are ready to measure within a microscope. And there we see advantages, and where I want to show you how we, for example, have our measurement set up. First of all, we stay in liquid. It's a clear, easier approach, because all we need to do is, when the particles are in liquid, we need to make sure that they're not too big of particles in there. If, for example, they cannot block it anymore, or you can directly measure the particles when you have a liquid already and not being too kind of big, of containing too big particles. But then it's really, you put the tube inside your sample container, and you're able to turn on the device and start scanning with this flow-through Raman tweezer base. You generate different outcomes. You have, this is, for example, we measured with different samples, with different particle systems to really generate all these different outputs. And we also knew that not only the spectra needs to be measured, but you also need more information on what kind of spectra. So we are building in really the different spectra databases, which are in the community now collected, to have degraded spectra, to have different polymers, to have a database that we compare and give a, so to say, rate on how much they really compare to the spectra when they flow through. Of course, with standards like shown here, it's easy, but I will show you that it also works with different spectra like what we did here. We were first looking on what kind of certified reference materials are out there, and we noticed there's not as much as we thought that to really have different polymers, different sizes, and different concentration particle systems out there where we can basically define our system and give a clear performance qualification. So we had to really work and look for people who can provide us with different samples and different materials and different sizes. And so we were able to, for example, create this PMMA and polystyrene mixture and start screening. And this is one of our first measurements to really see, oh, we are able to clearly identify the different spectra, and we are able to really do this over time. So the first step was, so to say, done, that we are able to define all the different spectra, measure them over time, and get information on the different occurrence. We thought, is this also possible with real samples? So one of our physicists, he bought a salt shaker, grinded some salt because he knew, okay, there is a POM milling kind of contraption in there, and the salt was then put into water, and we started scanning and was clearly able to also define POM, for example, on this milling salt shaker. Same, we found some raman-plastics where we, for example, had only the drinking water and being touched by this rubber kind of container lids, and we were able to refine those contaminations as well when we tried to see how much particles are in there, but we found lots of contaminants coming from the lid as well. So we thought, oh, okay, so quality assurance during the measurement is also very high importance. The next thing we thought is, how far can we go down with our system? And there, again, we looked into standards and said, okay, when we look, for example, in this Thermo Fisher Scientific, and we knew that for sample characterization, we have this available already, we put different sizes in there. And one of our physicists said, okay, for 600 nanometers, it's still able to clearly define, for example, polystyrene standard and compare it to literature. So the information is there. So with our definition here of limit of detection for plastics, currently, we say it's roughly 600 nanometers. However, you need to already look a little bit longer onto the particles to create enough signal to noise to get this information. So we're defining the limit of detection with 600 nanometers, but limit of quantification, which I will show you later, a little higher. For other materials, we did this together with the University of Graz, titanium dioxide, which is also very abundant in the environment. We see that the Raman scatter is way bigger, but we go here really compared to the ICP-MS TOF, which created a size roughly in the 250 nanometer size regime. And we were also able to get clear Raman spectra on the particles we could identify, and could also see that the phase of the titanium dioxide was in this case really an anatase match. And we compare this to the reference materials. So also in this size regime, we are active, but for plastics, we need to have a little bigger particles on hand. One of the exciting things is now, okay, we knew now that we can measure particles. We can use the technology to scan particles, to differentiate particles, but you really need to know how many particles do you find. So the recovery rate is really important. And coming from pharmaceuticals, you always need to have some kind of performance qualification. And we knew that pharma counts exist. So there is a clearly count standard where a certain concentration per volume is in here. And we use this sample to spike. So we went downstairs, we took some really soil or like some water, clearly contaminated with soil, with different other components. And we knew that this sample has a clear, it's polystyrene again, and a clear concentration. And we knew when we measure the particles, first of all, we saw that taking this sample, lots of other particles are in there. So most of the particles are in this very small size regime. We used our normal characterization regime. We saw, of course, some very low concentrated bigger particles. And but most of the particles are really very, very small. So it really exponentially goes with size up. But some of the particles we put in there, we could clearly define, yes, we knew that we put 1,500 particles per milliliter into the sample. And we were wondering how many of them do we really see when we do, for example, a 50-minute scan. So we calculated how many should we find. And we calculated we should find roughly 23 particles for this recovery rate. We found 19. So calculating this, of course, within 15 minutes, the statistics, of course, if you scan longer, become better. But recalculating this estimated polymer concentration, we came to really a recovery rate of 1,170 particles per milliliter, and we expected 1,500. So this gives us a first indication that, yes, also recovery rate works, even when we have lots of other particles there. We found some other particles over time, so really the random distribution of the particles when we scanned those 15 minutes of the polystyrene, which we knew they're in there, but also some other CH bond potentially particles, as well as other weak Raman scatterers where our signal to noise ratio detected information coming more than just being more than noise, but also having, of course, particles in there with fluorescent signals or other particles with some clear indication. This could be beta carotene and so on. In order to do another real example to really see if this also works for other things, we used, for example, here some pharmaceuticals like oil and water emulsion product. We also put 5 micrometer particles in there again and looked at the size distribution. So there were bigger particles in there. We could also detect some bigger ones at the aggregation state, but then also were able to find our particles within this couple minutes scan. And we recalculated the polymer concentration and could actually see that the recovery rate is, of course, not very highly statistically relevant within the short minutes, but the recovery rate over time really showed, yes, we can see the particles, find them again, even though lots of other particles, in this case, like 30,000 particles, are still there, and we see the ones we actually want to find. We also see other ones. The particles we want to find generate really still very nice spectra. So also the standard deviation of all the different spectra is still very nice. And of course, there are other particles in there, fluorescent signals again, and other information on particles, which we do not really know what they are yet, but we could refine them in this kind of experiment. So with this, we thought, okay, if we have clearly defined particles for our performance qualification of this device, what about real samples? And real samples are less pronounced in their spectra. They are aged. Their conformation is different. Their shapes are different. So together with the University of Graz, we looked into this, that we really find a performance qualification of our device of, yes, we need to prove that with normal particles, we can measure, but also when they are really degraded. And this is what we did here. We used ozone. Ozone is creating these particles, stress on these particles and age them over a very short amount of time. And we scanned lots of particles. We put them through this ozone chamber, and we did not turn on the ozone. So we were able to, within this 140 seconds, we were able to really measure this 113 particles with very homogeneous spectra. So really a real-time approach. And we were able to really see the size distribution, so a count and a size distribution, and this all in real time. When we turned on the ozone for 5 minutes, we already saw that, first of all, we see information on the spectra. They start to change. The peaks are not as well pronounced anymore, but also fluorescence is starting to appear. The count goes down. So, and the size really changes from this 5 micrometer peak down to 4 micrometer peak, and also going further down. When we then put this into 10 minutes and 15 minutes, first of all, count really goes down, so the concentration changes. size distribution changes, and also fluorescence has a very different signals acting, but peaks are still very clearly definable. So we were able to see what kind of particles they are. And the size distribution really went down, and also clearly showing that our system is still able to track them and identify them when they are clearly below this 1 micrometer, so 600, 700 micrometer size regime. And we were able to really see this, follow this process and get information on H particles. So with this, we can also provide H particles in different shapes, in different kind of spectra areas, and use them for further investigations, and also get information on recovery rates also with H particles. And this will be the next things we are going to do with a system like this. But here we really wanted to show that information on concentration, information on size distribution, and clearly identification on spectra side is possible in a very short amount of time. With this, I want to also talk a little bit about the next steps and challenges, because of course, each and every method you develop has some initial setups and initial considerations you need to understand and of course further work on. And we also see this as the brave way to really make challenges into chances, because with this approach, really focusing on this 20 micrometer and below area size regime to really get in a very short amount of time information, this is a really chance to help the community, to help us as human to basically create this new technology and help getting information doing this. We also do this with cooperation partners like the University of Graz, also being funded by ERC, to really have all of this information on the Raman and the detecting of the particles and looking into the H particles, but also hyphenating this with ICP-MS TOF. So this is one of the next steps, working together with David Classes, that we connect. Here is our OF2I Raman device with this ICP-MS TOF single particle analytic technique to get information. How many particles carry heavy metals? How many particles do we really see, and what is their size? What is the spectral information before you have elemental composition available, and getting the information of both worlds, so to say, use their both strengths and get this as a hyphenation kind of area. We have started doing this, really also hyphenating the two technologies, getting information, trapping the particles, getting information, trapping particles size-wise, getting the Raman signals, and getting rid of the background signals, because we are able to really hold up particles in our cells and do all this over time and get rid of a contamination background to increase the strength of this ICP-MS TOF to really have a clear, better signal-to-noise ratio, and also to look into very low concentrated samples. David, for example, is really looking into ice cores, identifying particles, identifying if what kind of time periods are, for example, plastics already detectable, looking into the single particle analytics, getting different information on what kind of particles are out there, and using really OF2I ICP-MS TOF to get information on elemental composition, but also size and Raman analytics. So a real combination to get this approach going, to really develop this new technology. Another challenge or next steps we are working on is another hyphenation, where we combine OF2I with SEC. This can be really helpful to also get information not only on plastic contamination, what is, for example, coming down from filter material, but also aggregation information as a total. So hyphenating UV signals, giving you the information on what material is coming down, but also then looking into a clear over time information on what kind of particles are contained in this material really help, for example, in this case, to get very pure fractions for these cryo-EM studies, where we, for example, get information on bigger particles and smaller particles and define the best fraction looking further into. We were able to really identify aggregates coming from LDL using our Raman technology. So With this, I also think that through this flow-through principle, we are not only able to see what kind of contaminants, human samples or in human plasma and so on are in there, but also what kind of aggregates, and looking further into really clear populations, clear fractions, and using this technology of combining and looking into pure samples with the static light scattering, but also really looking into the particles themselves. What is there? Where do we have really small particles and the ones we have, and where do we have aggregates? We were further analyzing this then with, for example, to really see the subfractions, even though there are no aggregates, we were able, yes, this is really LDL. Please take this kind of fraction. It's pure sample, or it contains aggregates for example, here, this study where we did this on a single particle aggregation. The challenges, well, when we look into 50 micrometers and we look into 1 micrometer, for us, 1 micrometers are the particles we're used to, and it works really well. 5 micrometers, sweet spot. 10 micrometers is still something we can really nicely handle. But when we really want the one, we call it all sizes fits one challenge, we want to create this 1 to 550 micrometer space. There, we face some challenges because the particles, basically, when they are flow through, we need a high scanning speed. So we push lots of particles through, lots of volume through to get statistical valid data. But on the other hand, you also want to have particles available for a longer time when they flow through here and to get the information. When you, for example, then put a big particle, like a huge one, it stops, it's really trapped. And the smaller ones, they do exactly what they should do. They basically come, they are trapped, they flow through, we collect their data, and they flow out again. So with this, the challenge is to handle all the different ones, and we do this with our MATLAB script to get this information out yet, to collect the data from the flowing ones, and also to collect the data from the standing from the big ones. And when we do this now, we are now doing all the big ones and the small ones in one kind of evaluation step, so we can have this one all size fits one challenge solved and get really from 1 to 20 micrometers, but also the big kind of particles from 20 to 50 micrometers in a very continuous kind of way, where we handle the trapping mechanism and also make a clear dynamic kind of speed change, for example, in the pumping speed to pump them out for collecting this data. The second thing is sedimentation. As soon as particles get bigger, they also might sediment. So this is also something which for smaller particles is not as relevant, but there we need to really think and tackle this challenge. We have different approaches to really not only increase pumping speed and then push and pull, so to say, that they stay afloat. There we also create different shaking mechanisms and so on, that we tackle this challenge to really have a clear identification and also bigger ones, even though they sometimes sediment in a time frame where when they come in and are measured and come out, so that the information and the concentration is still right estimated also for these big ones. And one of the big challenges, I would say, also for Raman microplastic analytics in Raman microscopy or in other microscopy scanning mechanisms, is statistical kind of representative random sampling challenge. Because when you go down to 1 micrometer, also a filter with a diameter of 2 centimeters takes ages to scan. So they also need to think about how to statistically get valid data out of there and create a random sample to have information there. And when we do this, we also really need to check how many particles, when we have, for example, a certain concentration, a certain information on this is how many are in there, how many do we suspect, because we do not see each and every particle. Some particles also flow up here and are not trapped. So we can calculate how many we are supposed to see and how many do we actually see. And we need to look into different concentration ranges. So where we looked at, okay, when we put 400 in there, we are supposed to see this many. When we put 4,000 in there, we are supposed to see this many. And how many can we actually recover? So this is also something we need to really look at to guarantee for our performance qualification to have this statistical random sampling available. and to clearly prove with certified reference methods, materials, that we are able to do what we can do. So with this is what we work on right now. And one of the big challenges is to have certified reference materials available, that we can say our physical models give this and our experimental values prove that physics basically works, and it works for each and every population, it works for each and every concentration range, and we can prove this with real statistical samples. I think we are up for this challenge, and the community is also really looking into providing this statistical relevance, providing certified reference materials to do exactly this, to provide reliable data and also inter-technology comparison, but also, of course, performance qualification for inter-lab comparisons. And this is what basically we are really looking into. Advancing the state of the art also means to go really new ways in how to measure sizes from all the different signals we collect, from speed, from the trapping efficiency, from the excluded volume of particles when they flow through. And with this, physics is at work. We measure and we have lots of fun of doing it and really providing a clear approach, always based on clear physics, on how to give information on size, how to give information on population, and how to provide for you relevant data, what we basically can see in a previous example where we spiked, where we did the different populations, and where we used aging as demonstrating the capabilities. So with this, I hope I could tell you a little bit about the different challenges where we really had different mixtures of samples, where we had really scanning over seconds and minutes in order to quantify 20 and even below 1 micrometer, where we had the different matrix effects in having the presence of an emulsion product, having the presence of lots of other particles coming from soil, where we had the presence on really degraded particles. And I hope I could show you that there might be a way with OF2I Raman to break the size limit, to have this in a very fast and not as time-consuming way, and to get still size distribution, but also counting information in a very statistical manner, and doing this with a minimum on sample preparation. So with this, I hope I could show you how OF2I Raman has been used in different case studies, in different determination of different materials, in the determination of really very small sizes. I hope I could show you that we really want to go the way of proving the performance on these traceable standards wherever we can and wherever they're available, and where we want to also have something available where you are able to define your protocols, your SOPs using our device and getting reliable data out of it. As a brave solution, and this is now really the summary, we see ourselves getting this gap tagged, this gap closed, of going beyond this 5 micrometer or 1 to 20 micrometer size regime, providing a clear information in minutes rather than days or even months, and having a very optical, non-destructive option available with ease of use, simple preparation of your sample, and really just putting in the tube into your sample and start to scan and get the different polymer information as a count-based information out. So with this, I want to tackle the last thing. Our vision is always processes. And processes, not only in microplastic, starting with lab environment and having the information on a lab environment to really get information on the different samples is necessary. But in the long run, we see ourselves as really having production monitoring, water treatment monitoring, really getting information on a continuous way with this flow-through principle, creating, again, what we also do in pharmaceuticals and in biopharmaceuticals, having this lab-to-PAT approach. And this is really our long-term vision, to be able to give information worldwide at entry points, getting quality and getting the amount of contaminants on a particle base for deriving regulations getting clear monitoring for environmental issues and concerns, and give us the information for a healthier and safer world. And with this, I want to say that we are up for the challenge, creating this challenge for nano and microplastics, and it very well fits into our brave mission to really advance human well-being and igniting curiosity for research in providing insights for particle processes, drive innovation, and ensure a healthy and safer world.